The first airplane was not one in the sky first. It was one in a box of moving air in Dayton, Ohio. That claim sounds backward because the image most people remember is open air, dunes, wind, a fragile machine, and Orville Wright lifting from the sand at Kitty Hawk. But before that brief powered flight in December of 1903, the decisive struggle had already moved indoors. It was fought over numbers, over lift and drag, over whether respected tables could be trusted, over whether a wing that existed on paper would actually hold a man in the air. The uncomfortable question at the heart of the Wright story is not simply, how did two bicycle makers learn to fly? It is sharper than that. What if the best published information available to them was partly misleading when applied to their machine? What if the celebrated authorities were not wrong in every sense, but wrong enough in the wrong place to send a glider sinking through the air with only a fraction of the lift its builders expected? That is the contradiction that pushed Wilbur and Orville Wright toward their breakthrough. They did not begin by rejecting science. They began by reading it, respecting it, and using it. They entered aviation through the published work of earlier experimenters and theorists. They studied the problem as carefully as men working above a bicycle shop could study it. And yet, after their early gliders failed to match the predictions they had relied on, they faced a choice that would define the entire race to flight: trust the authorities or test the air for themselves. By the time the Wright brothers built their wind tunnel in Dayton in the fall of 1901, they had already been humbled by the wind. Their gliders of 1900 and 1901 had not performed as expected. NASA states that the 1901 glider produced only about one-third of the lift predicted when using Lilienthal-based data. That is not a small disappointment. That is the kind of error that changes the meaning of the entire experiment. A glider that should have soared was reluctant. A wing that should have carried weight did not carry enough. A calculation that should have guided design became a suspect. For Wilbur and Orville, the problem was not theoretical in the distant academic sense. It was physical. It was felt in the body of the pilot, in the awkward launch, in the machine's refusal to behave. At Kitty Hawk, in the Kill Devil Hills area of North Carolina, they had gone looking for steady coastal winds because Dayton did not offer suitable conditions for full-scale glider experiments. The Outer Banks became their outdoor laboratory. But the wind there did not merely test their machines. It tested their assumptions. They had divided the problem of flight into parts: lifting surfaces, control, and propulsion. That approach echoed an older aeronautical tradition associated with Sir George Cayley, who had separated the fundamental problems of flight long before an engine-powered airplane existed. But the Wrights made one priority especially clear. They did not believe flight would be solved by power alone. They believed a pilot would have to actively fly the machine. Control was not an accessory. It was central. That belief already set them apart from a simpler dream of flight: build a large wing, attach a strong engine, and let power overcome the rest. The Wrights understood that a flying machine had to be commanded in unstable air. It had to respond. It had to be balanced and steered. A machine that could lift but not be controlled was not a successful airplane. It was a hazard. Still, control could not solve everything. Even the best pilot could not command a wing that did not produce the expected lift, or a design crippled by drag. The Wrights needed reliable aerodynamic data, and at first they used the data available to them. That included the work associated with Otto Lilienthal, whose tables were among the respected sources in the existing aeronautical conversation. The brothers did not begin as isolated tinkerers guessing in a vacuum. They were readers, correspondents, builders, and experimenters, entering a field already crowded with claims, and they were not alone in that field. At the Smithsonian Institution, Samuel P. Langley represented a very different path to flight. Langley was secretary of the Smithsonian. He had achieved successful powered model aerodrome flights in 1896, and his work carried institutional weight, technical ambition, and public significance. Compared with two brothers from Dayton working out of a bicycle shop, Langley's effort looked better positioned to win. His full-scale human-carrying great aerodrome would later be launched from a houseboat on the Potomac River in 1903. It would fail in 2 attempts that year, and the National Air and Space Museum states that it proved incapable of flight in those attempts. But before those failures, Langley stood as a formidable rival in the broader race. That rivalry was not just a contest between men. It was a contest between methods. Langley's program was tied to a major scientific institution. The Wright's program grew out of workshop discipline, field testing, and eventually a homemade wind tunnel. Langley's effort had the aura of official science. The Wrights' work had the character of relentless measurement by outsiders who were willing to doubt even the numbers they had once trusted. The conflict was not crude. It was not ignorance against expertise. The Wrights depended on expertise. Wilbur Wright would write to the Smithsonian on May 30th, 1899, asking for publications that could help him study human flight. The Smithsonian would recommend works including Octave Chanut's Progress in Flying Machines and the Aeronautical Annuals. Those sources helped give the brothers a foundation. Without the published conversation, there would have been no Wright program in the form we know. But the deeper question was whether published knowledge was enough. The 19th century data available to them had not been created for every possible wing shape and every possible flying machine. The Wrights would later discover that Lilienthal's data was largely valid for Lilienthal's own wing geometry, but not directly transferable to the long, thin, rectangular planform they were developing. That distinction mattered profoundly. Data can be true and still be dangerous when used outside the conditions that produced it. A table is not the sky. A formula is not a flight. One number captures the tension especially well: the Smeaton coefficient, a numerical factor used in early lift calculations. The Wrights had used the widely accepted value of 0.005. Their glider results led them toward a value around 0.0033. NASA gives the modern accepted value as approximately 0.00326, close to the Wrights' revision. A difference that looks tiny on a page could decide whether a wing seemed adequate in calculation or failed to lift as expected in practice. This is why the wind tunnel mattered. It was not a curiosity or a side project. It was a weapon in a data war. Before the famous powered flight, the Wright brothers had to find out which parts of the inherited science could be trusted, which parts had to be revised, and which parts had to be measured again under their own conditions. After a bicycle wheel test on Dayton streets produced results that were difficult to control, they built a controlled wind tunnel environment. In October of 1901, after first trying a smaller experimental tunnel, they made a larger and more substantial one. It was an open return design, with a fan pushing air through an enclosed square box and out into the room. Inside that box, model wings could be mounted on balances. Lift and drag could be compared. Curves and proportions could be tested. Invisible forces could be made into readings. There's a quiet drama in that shift. At Kitty Hawk, the brothers had asked the natural wind to reveal the truth, but the natural wind was unruly. In Dayton, they forced air through a box and asked narrower questions. Which wing shape lifted better? Which produced too much drag? How did curvature matter? What did a long, thin wing do that a short, wide one did not? The wind tunnel did not make flight simple. It made ignorance measurable. And that is the war before the flight. Not a public duel, not a race marked by cheering crowds, but a struggle between authority and experiment, between elegant prediction and stubborn failure, between better-funded ambition and workshop verification. The Wright brothers' achievement at Kitty Hawk did not come from rejecting the work of others. It came from entering that body of knowledge, finding where it failed them, and building the means to correct it. They were not merely building an airplane. They were building confidence in the numbers that would allow an airplane to exist. To understand how that began, we have to move back before the wind tunnel, before the failed gliders, before the first powered flight, to a moment when Wilbur Wright reached out not with a machine, but with a letter. On May 30th, 1899, he wrote to the Smithsonian Institution asking for help. The war over the air began, in part, with a request for books. The request for books was not a small detail at the edge of the story. It was the doorway through which Wilbur and Orville Wright entered aviation as a serious study, not as a daydream. Before there was a glider on the sand, before there was a wind tunnel in the bicycle shop, before there was a machine powerful enough to carry a pilot, there was an admission of uncertainty. Wilbur Wright did not begin by claiming he knew how to fly. On May 30th, 1899, he wrote to the Smithsonian Institution asking for publications that could help him study human flight. That date matters because it places the Wrights inside an existing world of aeronautical research. The popular version of invention often prefers a cleaner picture: two brothers, a bicycle shop, a flash of insight, and then the airplane. But Wilbur's letter shows something quieter and more important. The Wrights began as readers. They began by asking what had already been tried, what had already been measured, what had already failed, and what the leading authorities believed to be true. They were not isolated from the conversation. They were trying to join it. The Smithsonian was a natural place to ask. It was not only a museum or a symbol of national learning. It was also connected to the most visible American aeronautical work of the time through Samuel P. Langley, the secretary of the Smithsonian. Langley had already achieved successful powered model aerodrome flights in 1896. His work stood for one path into the air, institutional, well-known, and backed by scientific prestige. Wilbur Wright, by contrast, was writing from Dayton, Ohio, from a world of bicycles, tools, and practical mechanics. The contrast is tempting to exaggerate, but it should not be misunderstood. The Wright brothers were not anti-intellectual craftsmen setting themselves against science. Their later triumph would come because they took published science seriously enough to test it. The letter to the Smithsonian is the first clear sign of that attitude. The Smithsonian responded by recommending sources that gave the brothers a foundation. Among them was Octave Chanut's Progress in Flying Machines. They were also directed toward the Aeronautical Annuals. These were not magical manuals with a hidden recipe for the airplane. They were records of attempts, theories, designs, measurements, and arguments. They gathered the work of people who had already spent years thinking about wings, lift, resistance, stability, and power. For Wilbur and Orville, that mattered. It meant they did not have to begin with a blank page. They could begin with a map, even if parts of that map would later prove misleading. Octave Chanut's role is especially important because his work represented the state of a shared investigation. Progress in Flying Machines was not merely a celebration of success. The title itself carried a careful promise: progress, not completion. Human flight was still unfinished. The machines described in such works were steps, experiments, partial answers. Some offered insights. Some exposed traps. Some showed how easily a design that seemed plausible on paper could fail when it met the air. The Aeronautical Annuals served a similar purpose. They gave the Wrights access to an aeronautical culture already wrestling with the same questions that would soon occupy them. What shape should a lifting surface have? How should a machine remain balanced? Could a pilot control a craft in changing wind? Was success mainly a matter of building a powerful engine, or did the deeper problem lie elsewhere? The brothers' later work can look so original that it becomes easy to miss this beginning. Their originality did not come from ignoring earlier investigators. It came from reading them closely, borrowing what seemed useful, and then, when experience contradicted prediction, refusing to pretend the contradiction was not there. That is why the letter to the Smithsonian belongs at the center of the story. It marks the start of a disciplined relationship with authority. At first, published authority was necessary. It gave Wilbur and Orville language, formulas, examples, and assumptions. It told them what previous experimenters had believed about air and wings. It helped them decide what problems had to be solved before flight could become practical. But authority also came with danger. A published number can feel more solid than it is. A table can appear universal when it is really tied to a particular wing shape, a particular experiment, or a particular assumption. The Wrights did not know that yet. In 1899, the problem was not to overthrow the literature. The problem was to understand it well enough to begin. Their path began, then, not with rebellion, but with apprenticeship. In Dayton, the brothers could read about earlier aeronautical efforts while remaining grounded in their own habits of work. Their bicycle shop was not a university laboratory, but it trained them in precision, adjustment, repair, and the consequences of small errors. A bicycle is a balancing machine. It demands sensitivity to control, friction, weight, alignment, and the human body. Those practical instincts would matter later. But the first move was still intellectual. Gather the best available information, study it, and reduce the mystery of flight into problems that might be attacked one by one. This is where the Wrights differ from the myth of the lone tinkerer. A tinkerer might simply build, fail, and build again. Wilbur and Orville certainly built and they certainly failed, but they did not treat failure as random.
They wanted a chain of reasoning.
They wanted to know what the air was supposed to do and why their machine did or did not match that expectation. The Smithsonian recommendations helped create that chain. Through Chanute and the annuals, the brothers encountered a field already shaped by experimenters and theorists. They learned that heavier-than-air flight was not a single problem, but a group of connected problems.
A machine had to be lifted.
It had to be balanced and controlled. Eventually, it had to be driven forward under its own power. These concerns had been discussed before the Wrights entered the field, and earlier aeronautical theorists such as Sir George Cayley had already helped establish the habit of separating flight into its essential functions.
For Wilbur and Orville,
This way of thinking was decisive. It kept the airplane from appearing as one impossible object. Instead, it became a system. A wing could be studied as a lifting surface. Control could be studied as its own question. Propulsion could be postponed until the rest of the machine made sense. The published literature did not solve those problems for them, but it helped show them that the problems could be separated. That separation would soon define their approach. There is also a quiet irony in the Smithsonian connection. The institution that supplied Wilbur with reading material was also the home of Langley, whose better-funded work would become one of the great comparisons in the race toward powered flight. Langley's powered models had flown successfully in 1896, and his full-scale effort would later become a symbol of institutional ambition. The Wrights, meanwhile, began with borrowed publications and a determination to understand. But in 1899, that rivalry was not yet the visible drama. Wilbur's letter was not a challenge. It was a request. He was asking for help from the very world of established knowledge that he and Orville would later have to question. That makes the moment more interesting, not less. The Wrights did not win because they stood outside the scientific conversation. They won because they entered it, learned its vocabulary, trusted it far enough to begin, and then tested it hard enough to discover its limits. The books and papers gave them more than information. They gave them a starting confidence that flight was not fantasy. Others had measured, glided, calculated, and designed. Others had failed in ways that could be studied. The air was difficult, but not unknowable. The challenge was to move from reading about flight to constructing a method for learning from it directly. That movement would take time. It would pass through kites and gliders, through the winds of Kitty Hawk and the sand of Kill Devil Hills, through disappointment with predicted lift, and finally, through a box of moving air in Dayton. But the intellectual pattern was already present in Wilbur's first appeal to the Smithsonian. Ask what is known. Study it carefully. Divide the unknown into pieces. Test each piece against the world. The brothers began, then, with respect for the record. They accepted that they were entering a conversation older than themselves, carried by names like Chanute and Cayley, collected in works like Progress in Flying Machines and the Aeronautical Annuals, and preserved by institutions like the Smithsonian. But reading also taught them that the airplane would not emerge from one grand stroke. It would have to be broken apart. Lift, control, propulsion. The problem was beginning to take shape. And the Wrights' most unusual decision would be to decide which of those pieces deserved their attention first. Lift, control, propulsion. Once the Wright brothers saw the flying machine in those terms, the dream became less mysterious, but not easier. It was no longer simply a question of whether human beings could rise into the air. It was a question of what had to be solved first, what could be borrowed from earlier experimenters, and what would have to be learned by direct trial. That way of dividing the problem had a history. Sir George Cayley, one of the earlier theorists of aeronautics, had helped frame flight as a machine problem made of separate functions. A wing or lifting surface would hold the craft up. A means of propulsion would drive it forward. Some system of control would allow the machine to be guided. This may sound obvious now, but it was a powerful act of simplification. It meant that an airplane did not have to imitate a bird in every detail. It had to perform the essential tasks that made flight possible. For Wilbur and Orville Wright, reading the older literature did not lead to imitation alone. It gave them a structure. They could ask, piece by piece, what the machine needed. How much lift would a surface produce? How would the craft be balanced? How could a pilot command it when the air shifted around it? What power would be needed after the glider had proved itself? The Wrights entered the problem through books, but they did not treat books as final authority. They treated them as a map of the battlefield. And on that map, their attention moved first toward control.
This was the unusual choice.
Many people looking at the flying problem might have been tempted to begin with power. If a machine could not stay in the air, perhaps it needed a stronger engine. If it could not move forward fast enough, perhaps it needed more thrust. Samuel P. Langley, the secretary of the Smithsonian, had already demonstrated successful powered model aerodrome flights in 1896, and his work represented a well-funded path toward mechanical flight. The engine, the launch, the thrust, the machine as a powered device, these were natural places for ambition to gather. The Wrights did not ignore propulsion. They knew that a practical airplane would need it. But they believed that power alone could not solve the deepest danger. A flying machine would not merely have to rise. It would have to be flown. That distinction is quiet, but it changes everything. To rise is to generate lift. To fly is to remain under command while moving through unstable air. The Wrights understood that the pilot could not be a passenger in a drifting object. The pilot would have to act. He would have to correct, balance, steer, and respond. In this view, an airplane was not a stable platform with a person sitting on it. It was a dynamic machine in conversation with the air, and the pilot was part of the system. This is one reason the Wright story is not only a story of wings and engines. It is a story of judgment. The brothers were trying to understand what kind of machine the air demanded. If the air were perfectly steady, if the craft always met it from the same direction, if every gust were absent, then lift and power might seem like the main problems. But real flight would not happen in still equations. It would happen in wind. A lifting surface might carry the weight of the machine, but a gust could tilt it. A turn could disturb it. One wing could rise while the other fell. Without command, a successful lift surface might only carry the pilot into danger. So the Wrights placed control near the center of the problem from the beginning. Their later system of wing warping, their movable rear rudder, and the hip cradle used in the 1902 glider would all belong to this line of thinking. Those later mechanisms were not accidental add-ons. They grew from the early conviction that the pilot had to be able to manage the machine in the air. Wing warping, in particular, showed how differently they were thinking. Rather than imagine a rigid craft that must remain automatically steady, they considered a flexible means of altering the wings so that one side could behave differently from the other. A pilot could use the machine's shape to answer the air. The later addition of a movable rear rudder connected to wing warping would refine that answer, helping the glider respond more coherently when the wings were twisted for control. But the principle came first. Control was not decoration. It was survival. This priority also explains why the Wrights were willing to spend so much time as glider experimenters before attempting powered flight. A glider stripped the problem down. Without an engine, they could study lift and control directly. They could place a human operator in the machine and learn whether the craft could be balanced and guided. Propulsion would add another layer of difficulty, but it would not make an uncontrollable machine safe. If a glider could not be flown, an engine would only make it fail faster. The division of the problem also protected the Wrights from a common kind of confusion. In a complicated invention, failure can come from many places at once. A machine might lack lift because the wing shape is wrong. It might descend because the calculations are wrong. It might seem unstable because the pilot has too little command. It might be promising in one part and defective in another. By separating lift, control, and propulsion, the brothers gave themselves a way to ask better questions. This method did not guarantee quick success. In fact, it would eventually lead them into deeper doubt. When their early gliders failed to perform as predicted, they would have to ask whether the problem lay in their surfaces, their control, their assumptions, or the published numbers they had trusted. But the habit of division made that investigation possible. They were not simply disappointed builders. They were experimenters trying to locate the source of error. That is why the Wrights' early emphasis on control should not be seen as caution alone. It was an engineering strategy. They were deciding that the first full problem was not how to attach an engine to wings. It was how to make a human-carrying craft answer its pilot. Lift could raise the machine. Propulsion could sustain forward motion. But control would decide whether flight could become repeatable, intentional, and survivable. In this sense, the Wrights' thinking was both respectful of older aeronautical theory and sharply independent. From figures such as Cayley and from the wider record preserved in the sources they had requested from the Smithsonian, they inherited the idea that flight could be broken into parts. But they chose their own order of attack. They did not let the glamour of power overwhelm the less dramatic problem of command. It is easy, after the fact, to underestimate that decision. The first powered flight at Kitty Hawk is remembered because the machine carried an engine and a pilot and moved under its own power. But the famous moment depended on a prior belief: the pilot was not cargo. He was an active agent. The craft had to be designed around his ability to feel, correct, and direct it. The Wright Brothers' bicycle work in Dayton, Ohio, may have reinforced that practical sensibility, though the central fact remains their aeronautical reasoning. A bicycle is balanced by a rider in motion. It is not merely supported, it is controlled. The Wrights approached the airplane with a similar respect for active balance. A flying machine would have to live in motion, and motion required response. Once they had divided the problem, the next question was where to test it. Dayton was their home, their workshop, and the place where ideas could be drawn, built, and argued over. But the control problem could not be solved on paper alone. A glider needed wind. It needed open space. It needed conditions strong and steady enough to let the brothers practice, measure, and observe. The air around Dayton was not enough for that purpose. If they were going to learn whether their lifting surfaces and control ideas could survive the real wind, they needed a different outdoor laboratory. That search would carry them away from the bicycle shop toward the coast of North Carolina, to Kitty Hawk and the Kill Devil Hills area, where the wind itself would become both partner and judge. Dayton could give the Wright brothers tools, habits, and a disciplined workshop culture. It could give them a bicycle business, metalworking experience, and a place where ideas could be turned into parts. But it could not give them the kind of air they needed. That was the practical limit of home. A glider was not a drawing, and it was not a small model held in the hands. If Wilbur and Orville were right that flight depended on active control, then they had to place a real machine into moving air and learn how it behaved. They needed wind strong enough to lift a pilot and steady enough to make repeated trials meaningful. The ordinary conditions around Dayton, Ohio, did not offer that. The brothers could build there, but they could not fully learn there. So the search moved outward. The place they chose was not a center of industry or a university laboratory. It was Kitty Hawk and the Kill Devil Hills area on the outer banks of North Carolina. In the larger story of powered flight, those names are often remembered for a later moment, the morning when the 1903 Flyer rose from its starting track. But before that famous flight, the Outer Banks served another purpose. It became the Wrights' outdoor laboratory. That word matters. Kitty Hawk was not simply a romantic background of sand and sea. It was chosen because it offered something Dayton lacked: steady coastal winds. For the Wrights, wind was not scenery. It was equipment. It was the invisible engine of their early glider work, the force that would test whether their assumptions about lift and control were usable outside the page. In Dayton, they could think carefully. On the coast, the machine would answer back. The move from Ohio to North Carolina also changed the character of the experiment. In the bicycle shop, the brothers could control materials, dimensions, and mechanisms. They could discuss wing warping, sketch arrangements, and build with the precision of men used to making machines dependable. But once a glider was carried into the wind, control became a shared matter. The pilot could command, but the air could refuse. The machine could be carefully made and still behave badly. A trusted calculation could appear sound in a notebook and then fail in practice. That was why the Outer Banks were so important to the story before the wind tunnel. The brothers did not go there because they already knew the answers. They went because they needed a place where their questions could become physical. A glider experiment asks a simple question in a severe way: will this surface carry weight in air? But for the Wrights, the question was never only about rising. Their earlier thinking had already separated the problem of flight into lifting surfaces, control, and propulsion. At Kitty Hawk and the Kill Devil Hills area, two of those problems could be studied without an engine. They could observe whether the wings lifted as expected, and whether a pilot could keep command of the craft in the wind. That made the coast a proving ground for both mathematics and judgment. The brothers had not abandoned the published authorities they had studied. They had entered aviation by reading, by learning from men such as Octave Chanute and from the accumulated work preserved in publications recommended by the Smithsonian. They understood that they were not the first to ask how air supported a wing. But reading could not settle everything. Published tables and formulas had to meet the same air that would meet the machine. The first lessons were therefore exposed, uncomfortable, and difficult to simplify. A coastal wind could be steady compared with inland conditions, but it was still real wind, not laboratory air. The sandhills could provide space, but not certainty. The brothers could watch, adjust, and try again, yet every trial carried the complexity of the open world. The angle of the machine, the response of the pilot, the strength of the wind, the behavior of the wings, all came together at once. This was the strength of Kitty Hawk, and also its limitation. It was strong because it forced the Wrights to deal with flight as a whole. A glider in the air could reveal troubles no drawing would reveal. It could show whether control was a living problem rather than an abstract one. It could test whether a person lying in the machine, shifting and commanding, might actually manage the motion of a craft in flight. It could turn theory into experience. But it was limited because the open air did not easily isolate causes. If a glider failed to lift as expected, what had failed? Was the wing badly shaped? Was the pilot's handling the problem? Was the wind different from what the brothers believed? Or were the figures they had taken from respected aerodynamic sources not as reliable for their machine as they appeared? Those questions did not yet point directly to a wind tunnel. They emerged slowly, through disappointment. The brothers had gone to North Carolina because Dayton was not enough, but the coast would teach them that even a better outdoor laboratory could not answer every question cleanly. This is one of the quiet turning points in the Wright story. The Outer Banks did not simply lead to success. They also produced doubt. Not the vague doubt of people losing interest, but the sharper doubt of experimenters who see a mismatch between expectation and result. The Wrights had brought with them an intellectual inheritance, equations, tables, and ideas developed by earlier students of flight. On the sand, those inherited numbers had to carry a machine. When the machine did not behave as predicted, the meaning of failure changed. A casual inventor might have taken poor performance as a sign that the dream itself was impossible, or that more power was needed, or that courage alone would eventually make the difference. The Wrights were moving in another direction. Because they had divided the problem, they could examine failure more carefully. Lift could be questioned separately from control. Control could be studied separately from propulsion. The coast gave them the experience needed to ask whether the trouble lay in the machine, the pilot, the conditions, or the data. Dayton had been insufficient because it lacked the right wind. Kitty Hawk was necessary because it supplied that wind. But necessity is not the same as completeness. The brothers needed the coast to expose their assumptions. Later, they would need a controlled indoor experiment to test those assumptions one by one. For now, the image to hold is not yet the powered flyer and not yet the square wooden tunnel in the Dayton shop. It is a glider on the Outer Banks facing coastal air that was more useful than the air at home and still not obedient. The brothers had come seeking steady wind, and they found it. They had come seeking a place where their ideas could be tested, and they found that too. But the answers were not the answers they expected. The Kill Devil Hills area would become associated with practice, persistence, and eventually triumph for all. Before that, it was a place of measurement by exposure. Every glide was a negotiation between theory and weather. Every imperfect result added pressure to a growing suspicion. If the wings were not lifting as the published figures suggested they should, then the problem might not be only in the machine. It might be in the numbers. That suspicion did not erase what the brothers had learned from earlier aeronautical writers. It made the debt more complicated. The Wrights were still part of the existing conversation about flight, but now they were beginning to argue with parts of it. The coast had given them evidence that could not be ignored. The wind had served as partner and judge, just as they needed it to. And its judgment was unsettling. Out of Dayton, they had carried a method. At Kitty Hawk, they gained experience. In the Kill Devil Hills area, they began to see that outdoor trials could reveal a problem without fully explaining it. The gliders would have to speak more clearly, and soon their refusal to match prediction would force the brothers toward a harder choice: keep trusting the accepted data or begin measuring the air for themselves. The harder choice began quietly, not with a public defeat, but with a mismatch. The Wright brothers had gone to the coast because Dayton could not give them the steady wind they needed. At Kitty Hawk and in the Kill Devil Hills area, the air was strong enough to test their assumptions in a way the bicycle shop could not. A glider could be lifted, balanced, handled, and judged. The wind could turn a calculation into an experience. It could also turn confidence into doubt. That is what made the glider work so important. The brothers had not arrived at the Outer Banks as men guessing blindly. Since Wilbur Wright's letter to the Smithsonian Institution on May 30th, 1899, they had entered the existing literature of flight. They had read from the world that came before them. They had drawn on respected sources, including work connected with Octave Chanute and the aeronautical research tradition preserved in publications such as Progress in Flying Machines and the Aeronautical Annuals. They had also relied on aerodynamic data associated with Otto Lilienthal, whose gliding experiments had made him one of the central figures in the study of human flight. So when the Wrights built and tested their early gliders, they were not merely asking whether wood, fabric, and wire could rise from the sand. They were asking whether the accepted numbers could be trusted at full scale, in real wind, under the hands of a pilot. Their machines carried more than structure. They carried the authority of tables, formulas, and inherited confidence. And then the gliders refused to obey. The research path from 1899 through 1901 had begun with study, moved into design, and then into exposed trial. Each stage was supposed to make the next one clearer. The kite and glider experiments were meant to test control and lift under real conditions. The brothers had already decided that control mattered deeply, that the pilot would not be a passenger, but an active part of the machine. Yet even that disciplined approach could not protect them from a more basic question. What if the wing itself was not lifting as the formulas said it should? The disappointment sharpened after the 1900 and 1901 gliders failed to perform as predicted. The issue was not simply that flight remained difficult. The Wrights expected difficulty. They expected awkward landings, uncertain handling, and the hard schooling of wind and sand. What troubled them was that the machines did not match the aerodynamic expectations they had carried into the experiments. A glider that behaves badly can be blamed in many ways. Perhaps the pilot has not mastered it. Perhaps the structure flexes. Perhaps the wind is not what it seems. Perhaps the design has been built imperfectly. Early aviation was full of such uncertainties, and outdoor testing made them worse. A gust could masquerade as a principle. A moment of control could vanish before it could be measured. The Kill Devil Hills area offered better wind than Dayton, but it did not offer a perfectly ordered laboratory. It was still the open air, and the open air rarely explains itself. Even so, the results were too large to dismiss as ordinary experimental confusion. NASA states that the 1901 glider produced only about one-third of the lift predicted when using Lilienthal-based data. That was not a small difference. It was not the kind of error that could easily be folded into rough handling or imperfect weather. A wing expected to lift with a certain strength was delivering only a fraction of that promise. The machine was not merely underperforming. It was contradicting the arithmetic that had justified its shape. That one-third mattered because lift was not an abstract virtue. Lift determined whether a glider could carry a person, whether it could sustain a glide long enough to teach control, and whether later powered flight would have any realistic foundation. If the figures were wrong, then every future decision built on those figures would be unstable. Wing size, curvature, angle, and proportion would all be suspect. The brothers might increase area, alter structure, or change their handling technique, but if the underlying data was misleading, they would still be designing inside a false map. Here the rivalry in the story becomes quieter and more intimate. It was not yet a contest in the public imagination between famous machines. It was a contest between trust and evidence. On one side stood published authority, the accumulated results of earlier aeronautical work, the tables and formulas that serious students of flight were expected to consult. On the other side stood the Wrights' own gliders, dragging through sand, rising less than expected, and forcing their builders to decide how much respect was too much rate. The easy response would have been to assume that the fault lay entirely with them. They were bicycle makers from Dayton, working far from the large institutions and better-funded aeronautical projects. The Smithsonian was connected to the literature that had helped start their study. Samuel P. Langley, the secretary of the Smithsonian, represented a very different scale of research ambition. Against that background, questioning accepted data could look like arrogance. But the Wright brothers' strength was not that they distrusted everything. It was that they allowed experience to disturb belief. They had gone to the sources first. They had not rejected the aeronautical conversation from the outside. They had entered it as careful readers, then as builders, then as testers. That sequence made their doubt more powerful. They were not dismissing authority because they disliked it. They were discovering that authority, when translated into their own machines, did not fully explain what the wind was doing. The 1901 glider became the turning point because its failure was specific. It did not simply say, "Flight is impossible." It said, "Something in the prediction is wrong." That distinction is crucial. A vague failure discourages. A measured failure instructs. When a machine produces only about 1/3 of the expected lift, the disappointment begins to point toward a question. Was the error in the data? Was it in the formulas? Was it in the way older data had been applied to a newer wing shape? The answer was not yet settled, but the brothers now had a reason to doubt the ground beneath their calculations. This is the hinge on which the whole episode turns. Before the famous powered flight at Kitty Hawk, before the refined glider of 1902, before the wind tunnel campaign in Dayton, there was this moment of refusal. The gliders would not confirm what the tables had promised. The wind did not flatter the published numbers. It exposed them, or at least exposed the danger of using them, without further interrogation. Failure, in this chapter of the story, is not an interruption. It is the instrument that changes the method. The Wrights had wanted the Outer Banks to give them practice and proof. Instead, the coast gave them a contradiction. That contradiction was more valuable than success would have been, because success might have let them continue with borrowed assumptions. The disappointing gliders forced them to ask whether the old figures could be applied directly to their own designs. There is a kind of discipline in accepting such a question. It meant the brothers had to resist two temptations at once. They could not simply surrender to authority and conclude that their machines alone were at fault. But they also could not throw away all earlier work in frustration. The task was narrower and more demanding. Isolate what had failed, determine which numbers could be trusted, and find a way to make the air answer more clearly than it could on the dunes. That is why the 1901 disappointment belongs at the center of the Wright story. It does not diminish their achievement. It explains it. Their path to flight depended not on an unbroken chain of success, but on the ability to notice when a respected calculation did not survive contact with the wind. The gliders that refused to obey became the machines that taught them what kind of inventors they would have to become. By the end of that season of disappointment, the problem had narrowed. The brothers were no longer asking only how to build a glider, or how to control it, or where to find wind strong enough to test it. They were asking whether a small numerical assumption inside the lift calculation had been carrying too much authority. The failure had moved from the sand into the equation. And once the question entered the equation, one number in particular would begin to look less like a settled constant and more like the hidden fault line beneath the wing. By the time the question had moved from the sand into the equation, the Wright brothers were no longer dealing only with a disappointing glider. They were dealing with trust. The coast of North Carolina had shown them that something in the accepted method was not matching the air. Their machine had not produced the lift they expected. NASA states that the 1901 glider produced only about 1/3 of the lift predicted when using Lilienthal-based data. That was not a small error at the edge of measurement. It was a warning that one of the foundations under the wing might be wrong, or at least being used in the wrong way. Among the suspects was a modest-looking number known as the Smeaton coefficient. It did not look dramatic. It was not a wing. It was not a control system. It was not an engine. It was a factor inside a calculation, a small numerical constant used in early aerodynamic lift formulas. But in the Wrights' work, as in the work of other experimenters, a constant could shape an entire machine before a single spar was cut or a single fabric surface was stretched. If the number was too large, the calculation could promise more lift than the air would actually provide. A wing that seemed adequate on paper might be weak in practice. A glider, expected to rise, could instead settle, drag, and disappoint. The accepted value the Wrights had used was 0.005. It had authority behind it, because it belonged to the inherited language of aerodynamic calculation. For men trying to enter the study of flight from a bicycle shop in Dayton, Ohio, such a number carried weight. Wilbur and Orville Wright had not begun by assuming that the published world was careless. They had written to the Smithsonian Institution. They had read. They had worked from the best sources available to them. Their early calculations drew on the aeronautical knowledge then in circulation, including data associated with Otto Lilienthal. The problem was that the air at Kitty Hawk and Kill Devil Hills did not seem interested in respecting the printed expectation. This is where the drama of the Smeaton coefficient becomes more than a mathematical footnote. In a lift calculation, a coefficient is a bridge between a formula and the physical world. It helps translate speed, area, and air pressure into an expected lifting force. Change the coefficient, and the same wing, moving at the same speed, can appear more powerful or less powerful. Nothing has changed in the wood or cloth. Nothing has changed in the pilot's nerve. But the predicted machine changes because the arithmetic changes. For the Wright brothers, that was not an abstract problem. They had to decide how much wing they needed. They had to decide whether a glider was failing because it was badly handled, badly shaped, or badly calculated. A value of 0.005 made the air seem more generous than their experiments suggested. Their glider's behavior forced them toward a lower figure, near 0.0033. NASA gives the modern accepted value of the Smeaton coefficient as approximately 0.00326, close to the Wright's revision. That closeness matters, but it should not make the story seem inevitable. The Wrights did not possess modern aerodynamic instruments. They did not yet have the controlled wind tunnel campaign that would later transform their work. They had disappointment, observation, and the stubborn habit of comparing expectation with result. The revised number was not a trophy discovered in a moment of certainty. It emerged because the old number would not fit the evidence. The difference between 0.005 and a value near 0.0033 may sound small when spoken aloud. Both are tiny numbers. Both begin with zeros. But the size of a number on the page is not the same as its power inside a formula. If a constant overstates the pressure of the air, every design that depends on it may be quietly optimistic. A lifting surface may be drawn too small. A glider may be expected to carry a pilot more easily than it can. A whole research program can drift away from reality by trusting a value that has become familiar. The Wrights' problem was made sharper by the fact that their failures were not theatrical disasters. Their gliders did not simply end the project. They taught by refusing to behave. The 1900 and 1901 machines had gone to the coast to answer practical questions. They returned the brothers to Dayton with a deeper uncertainty. Was the published knowledge wrong? Was Lilienthal's data wrong? Was the formula wrong? Or were the Wrights applying valid information to a different kind of wing? That last possibility would become important. The Wrights would later understand that Lilienthal's data was largely valid for Lilienthal's own wing geometry, but not directly transferable to the Wrights' long, thin, rectangular planform. The issue was not simply that one honored predecessor had made bad measurements. The issue was transfer. Data gathered from one kind of surface could mislead when applied too confidently to another. Invention was not only the act of building something new. It was also the discipline of knowing when old knowledge had crossed beyond its proper boundary. The Smeaton coefficient therefore stood at the center of a larger change in the Wrights' thinking. They had begun as careful students of an existing aeronautical conversation. Now they were becoming critics of its assumptions. Not critics in the easy sense of dismissing the past, but critics in the harder sense of testing it. They were learning that authority had to be placed in a moving current of evidence. A table could be respected and still questioned. A formula could be useful and still incomplete. A coefficient could be widely accepted and still wrong enough to mislead a machine. There is a quiet tension here between paper flight and actual flight. On paper, the wing exists as geometry and calculation. It has area. It has angle. It has a predicted force. But in the air, the wing becomes an argument with pressure, drag, balance, and control. The Smeaton coefficient sat between those two worlds. Too high a value, and the paper wing became overconfident. Too low a value, and perhaps a designer might overbuild, overcompensate, or misunderstand the available lift. The right number did not guarantee success. But the wrong number could guarantee confusion. For Wilbur and Orville, the question was also practical in the most immediate sense. They were not designing for display. They were designing for a pilot's body in moving air. Their machine had to lift, but it also had to be controlled. Their earlier emphasis on control did not disappear because lift had become uncertain. Instead, the uncertainties began to merge. If the machine did not lift as expected, then control trials became harder to interpret. Was a difficulty in handling caused by the pilot's system of command or by a wing that was not producing the promised force? A bad coefficient could blur every other lesson. This is why a small number could become a hidden fault line beneath the wing. It did not break visibly. It did not snap like wood under strain. It did not tear like fabric in a gust. It failed more quietly, by giving the mind a wrong expectation before the machine ever met the wind. When the glider then behaved differently, the inventors had to decide whether to blame themselves, the weather, the machine, or the assumptions. The Wrights' importance lies partly in what they did at that moment. They did not simply add more surface and hope. They did not retreat into admiration for authorities whose conclusions seemed safer because they were printed. They began narrowing the problem. The value 0.005 no longer looked untouchable. Their experience pointed toward a figure near 0.0033, and that movement was a sign of their larger method. When the facts did not fit the formula had to face the facts. Still, a revised coefficient alone could not answer everything. The brothers needed more than a new number. They needed a way to test surfaces under conditions they could repeat. The Outer Banks had given them wind, but not complete control over the wind. Outdoor trials had revealed the mismatch, yet they could not isolate every variable. Speed, angle, gust, wing shape, and measurement all tangled together in open air. The Smeaton coefficient had drawn their attention to the weakness of borrowed data, but the next step required something more disciplined than suspicion. Back in Dayton, the problem would begin to change form again. If the air outside would not give them clean answers, they would try to make air answer indoors. The path toward that decision passed through a rough experiment on city streets, using a bicycle wheel in motion, and then toward a more controlled device built in the workshop itself. The number that would not fit had done its work. It had made the brothers stop treating the wind as a mystery to be endured and start treating it as a force that could be measured. Back in Dayton, the question was no longer whether the wind could teach them. It already had. The wind at Kitty Hawk and the Kill Devil Hills had taught the Wright brothers that their glider did not behave as the accepted figures said it should. It had taught them that published tables, however respected, could not simply be carried into every new wing shape and every new machine. But outdoor air had also shown its limit. It could expose a contradiction without explaining it cleanly. A glider on the sand was a living experiment, but it was a crowded one. The machine moved, the pilot shifted, the wind changed, the angle varied, and every result came wrapped in uncertainty. The brothers could feel that something was wrong. They could estimate. They could compare. They could reason backward from disappointing lift, but the air outside would not hold still long enough to be questioned one variable at a time. That was the turn in the fall of 1901. The problem had followed Wilbur and Orville Wright home from North Carolina to Dayton, Ohio, and it entered the familiar world of the bicycle shop. This mattered. Their next breakthrough did not begin in a university laboratory or in the offices of a government agency or beside a heavily funded machine. It began in the same practical environment where they understood wheels, chains, balance, friction, alignment, and careful mechanical adjustment. The first step was not yet the wind tunnel. It was rougher than that and more exposed to the ordinary confusion of the street. The brothers tried using a bicycle wheel as part of a test on Dayton streets, an attempt to compare aerodynamic effects while moving through the air. The idea fit their world. A bicycle wheel could rotate. A bicycle could travel. Motion through still air could be made to stand in for wind passing over a surface. In principle, it was a way of bringing the question down from the sand dunes and into a form they could manage closer to home. But the street was still not a laboratory. The test produced results that were difficult to control. A bicycle moving through Dayton could not give the brothers a perfectly steady current of air. The speed was not easily held constant. The surroundings changed. The motion itself introduced complications. What had looked like a clever way to measure the invisible forces of air still left too much in doubt.
And doubt was exactly what they were trying to reduce. That failed. Neatness is important. The bicycle wheel test did not solve the aerodynamic problem, but it sharpened the experimental problem. It showed the brothers that it was not enough to create motion. They needed controlled motion.
It was not enough to watch how a surface behaved in air.
They needed to know the speed of the air,
The angle of the surface, the shape being tested, and the force produced, while holding the rest of the arrangement as steady as possible.
They needed repeatability.
This was the quiet divide between trial and measurement. At Kitty Hawk, the Wrights had asked the natural wind to reveal the truth.
On Dayton streets,
They tried to carry the experiment through the air themselves.
both approaches left the air with too much freedom.
The answer, increasingly, was to reverse the relationship. Instead of moving the wing through uncertain air, they would move air over a fixed wing.
Instead of chasing wind,
They would manufacture it.
so in the fall of 1901,
The brothers built a wind tunnel.
the first version was smaller and experimental. It was a trial instrument.
A way of discovering whether an indoor stream of air could give them usable comparisons among wing shapes.
The principle was simple in outline,
But radical in consequence. Create a controlled current, place a small model surface inside it, and measure what the air did to that surface.
the machine did not need to be grand. It needed to be honest.
It needed to answer the same question the same way when the conditions were repeated. The Wrights were not the first people to wonder about aerodynamic measurement, and they were not entering an empty field.
Their path had begun with reading.
With Smithsonian guidance, with Octave Chanute, with the Aeronautical Annuals, with Otto Lilienthal's data, and the broader inheritance of 19th century aeronautical thought.
But now the brothers were moving from the
Library and the field into their own controlled source of evidence.
They were no longer only students of published results. They were becoming producers of data.
This was not a rejection of earlier work in the crude sense.
It was more disciplined than that.
Their experience had shown that borrowed figures could be useful and still incomplete.
Lilienthal's tables
Had not simply become worthless because the Wright gliders disappointed them.
The later understanding,
Reflected in the research record, was more precise. Data valid for one kind of wing geometry could fail when transferred too directly to another.
a wing shape, a planform,
A proportion, a curve, an angle, all of these could change the meaning of a number.
the Wrights needed to know what applied to their machines.
A wind tunnel gave them a way to ask that question without waiting for the weather.
By October of 1901,
After the smaller experimental attempt, they made a larger and more substantial tunnel.
that date sits quietly in the
Chronology, but it marks one of the decisive changes in the entire story.
The famous powered flight
Still lay more than 2 years ahead.
The successful 1902
Glider had not yet proven the new understanding in the Kill Devil Hills.
The propeller work for the
1903 aircraft was still in the future.
but the method that would lead them there,
Was taking shape in a box of moving air.
the larger tunnel meant commitment.
It meant the brothers believed the indoor approach could produce better evidence than the street test and more controlled evidence than the dunes.
They were not merely making a demonstration. They were building an apparatus for a campaign.
The campaign would depend on small model wings, not full-size gliders.
That, too, was a powerful change. A full machine required time,
Material, travel, weather, and risk.
a model could be changed quickly.
One curve could be compared with another.
One proportion could be set beside its rival. A shape that looked promising in theory,
Could be tested before it was enlarged into a human-carrying glider.
the scale was small, but the stakes were not. Each model was a question.
Does this form lift well? Does it drag badly? Does it deserve a place in the next aircraft? Invention often looks, from a distance, like a sequence of finished machines.
The 1902 glider. The 1903 flyer. The aircraft on the sand. The pilot at the controls.
But in the fall of 1901, progress looked smaller and more repetitive.
It looked like building a device that could make
Air pass over a surface again and again.
It looked like comparing readings.
It looked like accepting that authority must be tested not once, but patiently, under controlled conditions.
The bicycle shop setting
Makes the turn even more striking. The Wrights' tools and habits came from a trade where balance and adjustment mattered.
A bicycle is unforgiving
When parts are misaligned. Chains, sprockets, wheels, bearings, frames, and riders all involve force and motion in practical contact. That world did not automatically solve aerodynamics, but it encouraged a certain kind of thinking. If a machine behaves badly, isolate the cause. If a part is uncertain, test it. If a measurement is vague, build a better way to measure.
The tunnel was the aerodynamic expression of that habit. It also changed the emotional shape of the work.
The disappointment of the 1901 glider might have led to abandonment, or to blind tinkering, or to simply building larger wings and hoping for the best.
Instead, the brothers chose a more severe response. They submitted their own assumptions to experiment.
They did not merely accuse the accepted coefficient or the old tables. They built a way to find out what their own wings were doing. That is why the wind tunnel belongs at the center of the rivalry before the first flight. The visible rivalry would later include names, institutions, and public claims. Samuel P. Langley's better-funded work at the Smithsonian would loom over the race toward powered flight. But this quieter contest was already underway. Workshop measurement against inherited uncertainty. The Wrights were not winning by having more money, more prestige, or a larger staff. They were winning a narrower battle first, the battle to make the air measurable on their own terms.
And the tunnel made repetition possible. A test could be run, then run again. A model could be altered. A reading could be compared.
If one wing shape performed better than another, the conclusion did not depend on a single gust on a North Carolina hill.
It could be checked inside the shop.
That was the great advantage. The brothers could begin to separate the wing from the weather. This did not make the natural wind irrelevant.
The real machine would still have to return to the Outer Banks.
A glider still had to be flown, controlled, and trusted with a pilot aboard.
But the questions taken back to the dunes would be different after Dayton. They would no longer be based only on
Published expectation and outdoor surprise. They would be shaped by a growing body of measurements made indoors. In that sense, the fall of 1901 was not a detour from flight.
It was the moment the Wrights found a new route toward it.
The bicycle wheel test showed them the problem of uncontrolled motion.
The small tunnel showed them a possible answer.
The larger October tunnel gave them an instrument worthy of sustained work. Step by step, the wind was being taken out of the realm of guesswork and brought into a space where it could be questioned.
The brothers had stopped asking the wind for favors. They had begun forcing it to answer repeatable questions.
Soon, inside that box of moving air, the experiment would become tangible. A fan driving the current, an enclosed passage guiding it, a test section holding the model, and a viewing window above where one brother could watch the balances turn invisible pressure into evidence.
The war before the first flight
Had moved indoors, and its battlefield had become small enough to sit inside a Dayton workshop.
The larger October tunnel
Changed the scale of the question without making it grand.
It did not turn the Wright brothers into
Institutional researchers with a formal laboratory around them.
It did not give them the resources of the Smithsonian
Or the public standing of Samuel P. Langley's work.
It gave them something narrower,
And in that narrowness lay its power, a controllable passage of air inside a Dayton workshop.
The wind tunnel
Was, in the plainest sense, a box for disciplining the wind.
Its design was open return.
Air was not carried through a closed circuit, circulating again and again through a continuous loop. Instead, a fan drove air through an enclosed square box, across the place where the model would be tested, and then out into the room.
The wind entered the experiment by
Force, passed through the tunnel, did its work on the small wing shape inside, and was released back into the shop.
It was simple in outline.
But that simplicity mattered.
The brothers were not trying to reproduce the sky. They were trying to isolate one part of the sky's behavior long enough to measure it. That was the quiet revolution of the apparatus.
At Kitty Hawk and the Kill Devil Hills, the Wrights had gone to the wind.
They had carried their gliders to the Outer Banks because Dayton did not offer the steady conditions they needed.
They had waited, launched, adjusted, and interpreted.
The coastal air had been useful, but it had also been untidy.
It arrived with gusts, with changing strength, with the large uncertainties that come whenever a full machine and a human body are exposed to weather.
Inside the Dayton tunnel, the relationship was reversed. The air was brought to them. It was narrowed, guided,
And made to pass over small models in a controlled space.
The same current could be used again for another wing. A shape could be changed. A reading could be taken. Another shape could follow.
Instead of arguing with the atmosphere across dunes and sand, the brothers could ask one small question at a time. The device itself deserves to be imagined at workshop scale. This was not a ceremonial machine built to impress visitors. It was not a polished emblem of a national program. It belonged to the world of the Wright bicycle shop, practical, compact, and made for use. The brothers were mechanics as well as investigators. They knew how to build things that had to function, not merely resemble an idea. The tunnel was part of that discipline. Its importance did not come from its size. It came from the fact that it made invisible pressure visible through consequences. The fan was the source of the current. It pushed air through the enclosed passage, giving the brothers a moving stream where no natural wind was required. The box shaped that stream into something that could be used. The test section gave them a defined place to put the model airfoils, and the balances inside that section would respond to the forces acting on those models. The entire arrangement turned an elusive problem into a workshop procedure. On top of the test section was a glass viewing window. This detail is small, but it brings the experiment into focus. One brother could look down through the glass while the air moved below. From there, he could observe the balance readings and record what the model was doing. The other brother could tend to the apparatus, adjust the setup, prepare models, or manage the sequence of tests. The viewing window made the tunnel not just a box of moving air, but an instrument that could be watched. That act of watching was essential. The Wrights were not simply building a wind-making machine. They were building a way to convert air forces into evidence that could be compared. The glass window belonged to the same logic as the fan and the test section. It allowed the experiment to remain enclosed enough to control the air, while still open enough to observation. The model could sit inside the current, and the investigator could see what the balance said without disturbing the flow more than necessary. In this sense, the tunnel was a kind of argument against vague confidence. Before the Wrights built it, they had relied on published aerodynamic data that seemed authoritative. Their gliders had exposed a mismatch between prediction and performance. The problem was not that earlier investigators had done nothing useful. The problem was that numbers and tables could not be treated as universal answers without being tested against the actual wing forms the brothers hoped to use. A machine that looked reasonable in a calculation might behave differently in the air. The tunnel gave the brothers a way to find out before committing to a full-sized glider. The open return design also reminds us how direct their purpose was. They did not need a grand closed system. They needed a steady enough stream moving through a known space. They needed a place where small wing shapes could be mounted. They needed readings that could be compared from one model to another. The air did not have to be perfect. It had to be more controllable than a gust on a Dayton street or a shifting coastal wind over sand. That is why the tunnel belonged so naturally after the failed bicycle wheel experiment. The bicycle wheel test had tried to bring measurement into motion outdoors, but the conditions were difficult to control. The tunnel removed the moving vehicle and kept the air moving instead. The model could stay in one place. The observer could remain in one place. The reading could be watched, written down, and repeated with another surface. A square wooden passage, a fan, a test section, a glass window. These elements may sound modest beside the later drama of Kitty Hawk. But the achievement of powered flight depended on precisely this kind of modest control. The Wrights had learned that an airplane could not be built only from courage, nor only from elegant theory, nor only from an engine strong enough to pull a machine into the air. A wing had to be understood in relation to the air actually moving over it. Lift and drag had to be measured, not as hopes, but as forces. The tunnel made that possible because it reduced the problem. A full glider in the wind involved too many things at once: pilot movement, control response, changing gusts, structural behavior, launch conditions, and interpretation after the fact. In the tunnel, the brothers could strip the problem down. The question could become, how does this small surface behave in this current? Then, how does a slightly different surface behave? Then, which one gives more lift, less drag, or a better combination of both? The apparatus did not solve those questions by itself. It required instruments inside it, and careful reading of those instruments. But it created the protected space in which those readings could have meaning. It turned the air from an outdoor adversary into a repeatable test condition. That was the crucial difference between a guess and a campaign of measurement. There is also a human intimacy to the scene. One brother looking through the glass, another managing the test. Small model wings waiting their turn. Air rushing through a box and spilling back into the room.
The sound of the fan.
The effort to keep the work orderly. Nothing about it suggests spectacle. Yet in that ordinary space, the Wrights were building a private court of appeal against the authorities they had once trusted. If a published table said one thing and the balance inside the tunnel said another, the brothers now had reason to listen to their own evidence. This was not rebellion for its own sake. It was disciplined doubt. Their earlier reading had brought them into the aeronautical conversation. Their glider failures had forced them to question parts of that conversation. The wind tunnel allowed them to participate in it not as borrowers of data, but as makers of data. They could test forms suited to their own ambitions, their own plan forms, their own developing ideas of a controllable flying machine. The box of moving air was therefore more than an aid to design. It was a change in authority. The Wrights had built a device that could challenge assumptions without rhetoric. It did not declare that old numbers were wrong. It simply held a model and a current and let the forces act. Then the balances answered. And those balances would become the heart of the work. The tunnel supplied the moving air, the enclosed passage, the viewing window, and the repeatable setting. But the real translation still had to happen inside the test section, where lift and drag pressed on small wings and were converted into readings a careful observer could record. The wind had been brought indoors. Now it had to be weighed. The wind had been brought indoors. Now it had to be weighed. That was the quiet problem at the center of the Dayton experiments. A current of air, by itself, did not solve anything. A model wing placed in that current might rise, twist, strain, or resist, but unless those reactions could be turned into numbers, the brothers would still be left with impressions. They had already learned the danger of trusting impressions too far. At Kitty Hawk and the Kill Devil Hills, the air had given them experience, but experience alone had not explained why the gliders failed to match prediction. Inside the wind tunnel, the Wright brothers needed a way to make the invisible visible without relying on guesswork. The force that lifted a wing and the force that held it back had to be separated, compared, and recorded. That meant the test section was not just a place where small wings sat in moving air. It was a measuring chamber. The most important objects inside it were not the fan or the wooden enclosure, but the balances. The brothers built separate instruments for separate questions. One was a lift balance. The other was a drag balance. The distinction mattered because flight was never a single force. A wing could appear promising because it produced lift, but if it produced too much drag at the same time, the promise might be false. A surface that pulled strongly upward could also resist forward motion so heavily that it would burden the machine. The Wrights needed to know not merely whether a model lifted, but how efficiently it did so. That is why the balances became the hidden breakthrough of the wind tunnel campaign. They changed lift and drag from hopes into measurements. In earlier aeronautical work, tables and formulas had carried authority. The brothers had used published data because that was the available path into a field already shaped by earlier experimenters and theorists. But after the disappointing performance of their 1900 and 1901 gliders, the question was no longer whether a table had prestige. The question was whether a figure worked for the kind of wing the Wrights were trying to build. The lift balance and drag balance gave them a way to ask that question directly. A model wing could be mounted in the test section. The fan could send air through the enclosed box. One brother could observe through the glass viewing window above and record what the balance showed. Then the model could be changed, or another model could replace it, and the comparison could begin again. This was a different kind of argument from the one that might be made in print. It did not depend on reputation. It did not require the Wrights to claim in advance that Otto Lilienthal's data was wrong, or that any accepted formula should be discarded. It asked a narrower question. Under these conditions, with this model, at this angle, how do the forces compare? The lift balance answered one part of that question. It responded to the force that made the airfoil act like a wing rather than a flat obstruction. Lift was the promise at the heart of flying machines. Without it, there was no flight. But the Wrights had already seen how dangerous that promise could be when expressed only as prediction. Their 1901 glider, using Lilienthal-based data, had produced only about 1/3 of the lift expected, according to NASA. That failure had made lift itself suspect as a calculated certainty. In the wind tunnel, lift could be tested on a small scale before being trusted on a large one. A model wing did not need to carry a person.
It did not need to survive a gust at the Kill Devil Hills.
It only needed to reveal how its shape behaved in a controlled stream. If one curved surface produced more lift than another, the balance could show it. If a change in form made the result worse, the balance could show that too. Gradually, a wing ceased to be an article of faith and became an object in a ranking.
The drag balance answered the companion question.
Drag was less glamorous than lift, but just as decisive. It was the resistance a wing offered to motion through the air. A flying machine did not merely need to rise, it had to move forward while rising, and every unnecessary resistance would demand more from the machine, the pilot, or the engine that had not yet been built. Here again, the Wrights were refusing a simple answer. A wing shape that gave more lift might seem better at first glance, but if that added lift came with too much drag, it could become a burden. The brothers needed to compare advantages against costs. The drag balance helped expose those costs. Together, the two balances made it possible to judge a surface not as beautiful, plausible, or traditional, but as useful. This was the discipline the tunnel imposed. The model wings were mounted in the test section, placed where the moving air could act on them in a repeatable way. The brothers could study one form, then another. They could observe how changes in curvature, plan form, or arrangement altered the readings. The test was small, but its consequences were large, because it allowed them to stop treating the wing as a single mystery. They could break it into measurable behavior. In that sense, the balances continued the same habit of mind that had shaped their whole approach to flight. They had divided the larger problem into lifting surfaces, control, and propulsion. Now, within the lifting surface itself, they divided performance into lift and drag. They were not trying to solve flight with one heroic leap. They were trying to make each part less obscure. The Dayton shop mattered because it allowed this patience. The wind tunnel was not a grand institutional machine. It was part of a workshop environment, built by men whose daily work was still close to tools, metal, wood, and adjustment. That setting did not weaken the science. It gave the work its particular character. The instruments had to be practical. The readings had to be repeatable. The results had to be useful enough to shape the next glider. There is a quiet drama in that kind of measurement. It does not look like a launch. It does not have the visual force of a machine leaving the ground. A balance moving in a test section is a small event. A model wing in a box of air is easy to overlook. But before the first powered flight, these small events were where the decisive reversal occurred. The Wrights had entered the wind tunnel campaign after a crisis of confidence in inherited data. They did not yet have the successful 1902 glider. They did not yet have the 1903 flyer. They did not yet have the engine, the propellers, or the famous photograph at Kitty Hawk. What they had was a way to make the air testify in pieces. Lift could be read. Drag could be read. A model could be accepted, rejected, or set aside for further study. The brothers could build their own table from their own tests, one entry at a time. And because the tests happened indoors, in the same controlled setting, the results could be compared with a seriousness that outdoor gliding alone could not provide. This was the hidden war before the first flight, not simply Wright against Langley or workshop against institution, but measurement against assumption. Samuel P. Langley's work at the Smithsonian carried public standing and resources. The Wrights' balances carried something quieter. They allowed two bicycle makers in Dayton to generate aerodynamic evidence fitted to the machine they intended to fly. Once that change occurred, authority began to move. It moved away from numbers accepted because they were printed, and toward numbers earned because they could be reproduced. The brothers were not abandoning earlier aeronautical work entirely. They were learning where its limits lay. A table could be valuable and still not answer every question. A formula could be useful and still depend on the conditions behind it. A wing shape could look reasonable and still perform badly when lift and drag were measured together. The balances made those distinctions possible. Each reading narrowed the field. Each mounted model became part of a larger comparison. The test section became a court of evidence where shapes competed under the same stream of air. The brothers could now ask which surface lifted better, which resisted less, and which combination might serve a controllable flying machine rather than an abstract ideal. That is why the balances deserve to stand near the center of the story. They did not fly. They did not look like wings.
They did not become famous artifacts in the way the Flyer did,
but they helped decide what kind of wing was worth building.
they translated pressure into data.
And data into design.
From this point, the campaign could expand.
Once the tunnel and balances were ready, the brothers needed subjects to test. Not one or two favored shapes, but many small wings, varied enough to challenge assumption and precise enough to compare.
In the Dayton shop,
Metal could be cut, hammered, filed, and soldered into airfoils. The invisible forces now had instruments waiting for them. What followed was a war of models, fought by surfaces small enough to hold in the hand, but important enough to reshape the path to Kitty Hawk. The invisible forces now had instruments waiting for them. What the Wright brothers needed next was not a single perfect wing, imagined in advance, but a crowd of candidates.
small surfaces,
Slightly different curves,
different proportions,
different thicknesses, edges, and shapes. The kind of variations that might look minor on a workbench, but could decide whether a full-size glider lifted cleanly or disappointed them again on the sand at Kill Devil Hills.
This was the next quiet escalation in Dayton. The wind tunnel did not merely allow a test. It allowed a campaign. The models themselves were modest objects.
Many were made from materials already available in the Wright bicycle shop. The brothers used strips of 20-gauge steel, about 1/32 of an inch thick.
They cut them. They hammered them. They filed them. They soldered them.
In another setting, these might have seemed like scraps of shop metal, shaped by hand between repairs, tools, and bicycle parts.
But inside the tunnel, each strip became a question posed to the air. How much lift would this curve make? How much drag would it cost?
Would a slight change in form make the surface better, or only more complicated? The scale of the work matters because it changes how we should understand the Wright's breakthrough.
They were not simply choosing between a flat wing and a curved wing. They were not making one inspired adjustment
After the failure of the 1901 glider,
They were building an experimental field.
one small airfoil at a time.
NASA states that the brothers made
Preliminary tests on between roughly 100 and 200 models, then selected about 30 for more detailed parametric studies. The National Air and Space Museum gives the same campaign a similar scale from another angle, stating that they conducted preliminary tests on as many as 200 model wing shapes and recorded formal data on nearly 50. The exact count depends on what is being counted: first trials, selected forms, formal records, or detailed comparisons.
But the meaning is clear.
This was not a casual series of shop experiments. It was a systematic search through possibility. That is why the phrase, 200 little wings, carries weight. Each model was small enough to fit the tunnel, small enough to handle, small enough to make from shop material. Yet together, they formed an argument against guesswork. The brothers were refusing to let one failed glider become a vague discouragement. They were breaking the failure into pieces that could be tested. This was the difference between disappointment and investigation. At Kitty Hawk and Kill Devil Hills, a full glider carried many uncertainties at once. Wind strength varied. Sand, slope, balance, handling, and pilot position all mattered. If the lift was less than expected, the brothers could suspect the equations, the airfoil, the coefficient, the proportions, or the conditions. The outdoor test gave them reality, but reality came tangled. In the Dayton tunnel, the question could be narrowed. A small wing could be placed on a balance. Air could be driven across it. A reading could be taken. Another wing, almost the same, but not quite, could follow. The brothers could compare the two. Then another. Then another. It was slow work, but it changed the nature of the problem. Instead of arguing from authority or memory, they could build a ranked body of evidence. The models also reveal something important about the Wright method. They did not have to wait for a factory, a government laboratory, or a university apparatus before beginning serious aerodynamic research. Their bicycle shop supplied more than income. It supplied habits, precision with metal, comfort with tools, a willingness to make, adjust, and remake. The shop was not separate from the science. It was the place where the science became possible. A strip of steel could be curved into an airfoil. Its edges could be shaped. Its form could be altered and compared. Solder could join parts. A file could refine them. A hammer could change the curve. These actions were not decorative craftsmanship. They were part of the experimental method. If the question was how shape affected force, then shape had to be made carefully enough that the answer meant something. The Wrights were entering a contest not only with other inventors, but with their own earlier dependence on published tables. Before the wind tunnel, they had leaned on aerodynamic data from respected sources. After the poor performance of their earlier gliders, especially the 1901 machine, they began to suspect that the numbers they had trusted did not describe their own wings well enough. But suspicion alone was not knowledge. The tunnel campaign gave them a way to separate one possibility from another. The large rivals in this story can make the Wright shop seem almost too small. Samuel P. Langley, working from the Smithsonian world, had institutional standing and resources the brothers did not possess. His powered model aerodrome flights in 1896 had already shown that unmanned powered models could fly. The Wrights, by contrast, were shaping small steel surfaces in Dayton and placing them in a box of moving air. But the contrast is precisely the point. The war before the first flight was not decided only by money, title, or public confidence. It was decided by who could turn uncertainty into reliable design information. In this stage of the work, each small airfoil served as a disciplined challenge to assumption. If a surface performed poorly, that failure was useful. If another performed better, that improvement could be measured. The models allowed the brothers to explore not only whether a wing could lift, but how different features changed the balance between lift and resistance. The important word is compare. The wind tunnel was not merely a proving device. It was a sorting device. The National Air and Space Museum's reference to formal data on nearly 50 shapes gives a sense of how the preliminary swarm narrowed into records. Not every model deserved the same attention. Some could be eliminated quickly. Others invited closer measurement. NASA's description of about 30 selected for more detailed parametric studies points to the same logic. The brothers were not simply collecting numbers for their own sake. They were searching for patterns that could guide a real machine. The word parametric may sound modern and clinical, but the underlying idea is direct. Change one feature. Observe the result. Change another. Compare again. In the Wrights' case, those features included the qualities of wing shape that would soon become central to the design of their next glider: curvature, proportion, and arrangement. The little wings were not miniature decorations. They were instruments of decision. This is why the model campaign deserves to stand between the balances and the final airfoil conclusions. The balances made measurement possible, but the models gave measurement range. A single wing on a perfect balance would have told the brothers only about that one wing. Dozens of wings, and perhaps as many as 200 in preliminary form, turned the tunnel into a map of alternatives. The brothers were not asking whether air had force. They knew it did. They were asking which shapes used that force best. There is also a quiet psychological turn here. After the 1901 disappointment, the brothers could have become more conservative. They could have clung more tightly to familiar data, adjusting only enough to continue. Instead, they made the problem larger in the short term, so that it could become smaller in the long term. They multiplied the number of little wings because the full-sized answer had to be narrowed from evidence, not hope. Seen from a distance, the great image of the Wright story is the flyer lifting from the sand at Kitty Hawk in December of 1903. But before that machine could exist, the brothers had to create a smaller battlefield in Ohio. A battlefield of steel strips and solder joints, of filed edges and repeated readings, of models that never carried a pilot, never left the room, and never became famous, but nevertheless helped decide the shape of flight. The campaign scale is easy to miss because the objects were so small. A full glider dominates attention. A powered airplane becomes a monument. A model wing can disappear into the hand. Yet the Wrights' achievement depended on the discipline to take these small things seriously. Each one reduced ignorance by a little. Each one made the next comparison sharper. Together, they formed a body of evidence strong enough to challenge published expectation and guide the brothers toward a new design. By the time the models had been cut, shaped, tested, rejected, selected, and recorded, the Wrights were no longer merely asking whether their earlier sources were wrong. They were beginning to see what kind of wing their own evidence supported. The next issue was not simply lift in isolation. A surface could lift more and still be a poor choice if it dragged too heavily through the air. The little steel wings had opened the deeper question: What shape of lift was worth having?
The little steel wings had opened the deeper question.
What shape of lift was worth having? Not what shape could lift the most in a moment, or what curve looked most promising on a drawing, but what surface could do useful work in the air without demanding too much in return.
That distinction mattered. The Wright brothers were not trying to win a contest of isolated numbers.
A wing that produced more lift but also pulled backward with greater drag could trap an aircraft in a different failure.
It might rise better, yet refuse to move efficiently.
It might look successful on one balance and disappointing on another. In the Dayton wind tunnel, this was the lesson that began to separate raw force from practical design.
The earlier tradition had already pointed the brothers toward curved surfaces.
Otto Lilienthal's work had helped establish that cambered wings, shaped with curvature rather than left flat, were important to flight.
The Wrights had taken that inheritance seriously. Their gliders were not flat boards pushed into the wind.
They were built around the idea that air moving over a curved surface could generate lift more effectively than air moving over a simple plane.
But after the disappointments at Kitty Hawk and the Kill Devil Hills area, belief was no longer enough. The brothers needed to know how much curve,
What kind of curve, and at what cost?
inside the wind tunnel.
Camber became something that could be compared.
The word itself describes the curvature of the wing surface. A flat surface has no camber. A curved one arches away from flatness. To an experimenter looking for lift,
The attraction is obvious. If curvature helps a wing press air downward and produce an upward reaction, then more curvature might seem better.
it would be easy to imagine the problem
As a simple race toward deeper and deeper curves.
The tunnel argued for caution.
The tests showed that curved surfaces produced more lift than flat ones. That was a confirmation of one part of the established understanding. But the same experiments also showed that curved surfaces produced more drag.
The wing did not receive the benefit for free.
As the curve helped the surface lift, it also increased resistance to motion through the air. The brothers were not only searching for a wing that would hold a machine up, they were searching for a wing that could hold a machine up while still allowing it to move forward.
This is where the Dayton campaign
Became more than a correction of a coefficient or a check on a published table.
It became a study in compromise.
Lift was essential, but it could not be treated as the only good. Drag was not a secondary inconvenience that could be ignored until later.
In a glider,
Drag shortened the flight and steepened the descent.
in a powered machine,
Drag would demand more from the engine and propellers.
the Wrights had not yet built
The successful powered airplane, but the shape they chose for a glider already carried consequences for the machine that would follow.
the wind tunnel balances made that compromise visible.
A model wing could be placed in the moving air, and its behavior could be read not as a general impression, but as a relationship between forces. A shape that seemed promising because it lifted strongly could be judged again when its drag was measured. Another shape, less dramatic at first glance, might become more valuable because it gave a better balance of lift to resistance.
The best wing was not
Necessarily the one that shouted the loudest on the lift balance. It was the one that answered both balances in the right proportion. NASA states that the Wrights settled on a 1/20th camber for their designs. In plain terms, this meant a relatively low camber, not a deeply arched surface.
That choice is revealing.
It shows that the brothers did not take the conformation of curved surfaces and push it to an extreme.
They accepted curvature.
But they disciplined it.
They wanted the advantage of a cambered airfoil.
While avoiding the penalty of excessive drag. The phrase 1/20th may sound small, almost too modest to carry much meaning. But in the context of the Wright experiments, it was the kind of measured answer the wind tunnel was built to produce. Their campaign was not about discovering one grand secret hidden in the air. It was about narrowing uncertainty. A little less curve here, a different form there, a more careful comparison between lift and drag. The tunnel changed the question from, "Does this wing work?" to, "How does this wing compare, and what does the comparison cost?"
The brothers also tested and analyzed the form of the curve itself.
The research notes point to variables such as parabolic curve and circular arc. These were not poetic descriptions. They were different ways of shaping the camber. A circular arc follows the logic of a circle's curve. A parabolic curve follows another mathematical form. To the eye, both may look like modest variations on a bowed surface. To the air and to the balances in the tunnel, those variations could matter. This was one reason the campaign required many little wings rather than a few dramatic prototypes. If a curved wing was better than a flat wing, the next question became, which curve? If a deeper curve lifted more, the next question became, how much drag did it add? If a particular curvature performed well on a small model, the brothers could compare it against another with the same discipline. The answer would not be decided by reputation, elegance, or habit. It would be decided by the measured behavior of air against metal. The shape of lift was becoming a technical choice. The same broad habit of comparison extended beyond a single airfoil surface. The Wrights tested or analyzed configurations such as biplane and triplane arrangements. They were not only asking how one wing should curve, but how lifting surfaces might work together. A biplane configuration placed two wings in relation to each other. A triplane arrangement added another lifting plane. These possibilities belonged to the larger design world the brothers had entered when Wilbur first wrote to the Smithsonian Institution and began gathering the literature of flight. But in the Dayton shop, such ideas could be examined through their aerodynamic consequences rather than accepted as promising merely because they offered more surface. Here again, more was not automatically better. More lifting surface could mean more lift, but it could also mean more drag and interference. The central lesson held: flight could not be solved by piling up advantages on one side of the ledger while ignoring the debts on the other. Air was not generous in that way. Every surface had a price. Every curve had a price. Every apparent gain had to be checked against what it took away. That made the Wright brothers' wind tunnel work quietly radical. They were not simply trying to prove that their preferred ideas were right. Their earlier gliders had already punished that kind of confidence. The 1900 and 1901 experience had shown them that a full-size machine could disappoint, even when built from respected assumptions. The tunnel was their answer to that disappointment, but it did not give them permission to believe whatever seemed encouraging. It forced them into a harder discipline, to accept mixed results. A cambered surface was better than a flat one for lift, but too much camber increased drag. A configuration with more planes might seem to promise more support. But the drag question remained. A curve might be mathematically neat, but it still had to pass through the test section and answer to the balances. In this sense, the Wrights were learning to think like aerodynamic designers before the airplane itself had fully arrived. They were not merely asking whether a wing could hold up a pilot. They were beginning to ask whether the entire machine could be made efficient enough to be controlled, glided, and eventually powered. The 1/20th camber was not an isolated detail. It was part of a larger movement away from assumption and toward a measured balance of forces in woe causation. The drama of this chapter in their work is easy to miss because it lacks spectacle. There is no launch from a hill, no crash in sand, no engine coughing into life. There is only the repeated placement of small model wings in a box of moving air, the observation of readings through a viewing window, and the slow sorting of shapes into better and worse. Yet this was where the future aircraft became less vague. The wing was no longer simply a surface with enough area. It had a character. It had a curve. It had a drag penalty. It had to earn its place in the design. The brothers' choice of a low camber curved airfoil shows how carefully they were listening to their apparatus. The wind tunnel did not tell them to abandon curvature. It told them not to worship it. It confirmed that lift could be increased by bending the surface, then warned that the same bend could make forward motion harder. That kind of answer was more valuable than a simple yes or no. It gave the Wrights a way to choose. And once the question of curvature had been narrowed, another shape problem waited beside it. The tunnel campaign was not finished with the wing. Camber described the curve of the surface, but the planform of the wing, its length and width, also mattered. The brothers still had to understand why a long, narrow wing could behave differently from a short, broad one, and why data from one geometry might mislead a designer working with another. Lift had a curve, but it also had a span. Camber had answered one question about the wing's surface, but it had not answered the question of the wing's outline. A curved surface could be too deep or shallow, useful or costly, but even the right curve still had to be spread across a particular shape. It could be broad and stubby. It could be long and narrow. It could have the same total area and still meet the air in a very different way. That was the next lesson waiting inside the Dayton wind tunnel. The Wright brothers were not only testing how much a wing curved from front to back. They were also testing how the wing's length compared with its width. In modern language, this is aspect ratio. A long, thin wing has a high aspect ratio. A short, wide wing has a low aspect ratio. Both might present the same amount of surface to the air. Both might look, in a simple calculation, as if they ought to carry a similar load. But the wind tunnel suggested that the air did not treat them as equals. This mattered because the Wrights had already learned the danger of trusting a number without asking where it came from. Their earlier gliders had been designed with confidence in established aerodynamic tables and formulas. Those sources had seemed respectable, especially the work associated with Otto Lilienthal. But the 1900 and 1901 gliders had not behaved as predicted. NASA states that the 1901 glider produced only about one-third of the lift expected when using Lilienthal-based data. That failure had pushed the brothers back into the shop, back to their balances, back to their small wings. At first, the disappointment could have been read as a simple accusation. Lilienthal's data was wrong. But the wind tunnel made the answer more careful than that. The Wrights came to understand that Lilienthal's data was largely valid for Lilienthal's own wing geometry. The problem was transfer. Data gathered from one kind of wing could mislead a designer using another kind of wing. A table could be useful and still not be universal. That distinction is easy to miss, but it was central to the Wrights' breakthrough. They were not merely rejecting authority. They were learning how to place boundaries around it. Lilienthal's results belonged to a particular geometry, a particular family of surfaces, a particular way of presenting area to the air. The Wrights were working toward long, thin, rectangular wings. They needed to know how those wings behaved, not how a different wing had behaved under different assumptions. Inside the tunnel, the brothers could ask that question directly. They could mount one model, measure its lift and drag, then mount another with a different proportion and compare the readings. The same shop that had shaped strips of metal into small airfoils could now turn wing planform into evidence. Length and width were no longer matters of taste or imitation. They became variables. The result was one of the quietest but most important findings of the campaign. Long, thin wings with high aspect ratio performed better than short, wide wings with low aspect ratio. This was not a theatrical discovery. There was no dramatic crash, no public demonstration, no crowd at the edge of a sandhill. It was the kind of discovery that appears as a difference in readings, as a pattern across repeated tests, as a preference that becomes harder and harder to ignore. But it changed the machine the brothers would build. The reason it mattered was practical. A flying machine could not be judged by wing area alone. Area told only part of the story. If two wings had roughly the same total surface, but one spread that surface farther across the span while reducing its width from front to back, their behavior could differ significantly. The high aspect ratio wing could offer a better bargain between lift and resistance. For men trying to build a glider first and eventually a powered airplane, that bargain was everything. The Wrights had already learned from Camber that more lift was not automatically better if drag rose too sharply with it. Aspect ratio extended that lesson. The shape of the wing in plan view could influence whether the surface worked efficiently or wastefully. A short, broad wing might give area, but the tunnel showed that area arranged poorly did not have the same value as area arranged well. This helps explain why the 1902 glider looked so different in its aerodynamic intention from the disappointing machine that came before it. NASA states that the 1902 glider had roughly the same wing area as the 1901 glider, but about twice the aspect ratio. That is a striking comparison because it removes a simple explanation. The Wrights did not merely solve the problem by adding much more surface. They reorganized the surface. They changed the proportions. The same amount of wing, spread differently, could become a better wing. That lesson could only emerge once the brothers stopped treating published data as if it floated free from the geometry that produced it. Lilienthal's tables had not been meaningless. They had helped create the aeronautical conversation the Wrights entered. But the Wrights' tunnel work taught them that data carried a history. It came from particular models, particular surfaces, particular measurements. When moved too far from that original context, it could become dangerous. In that sense, the wind tunnel was not only a measuring instrument, it was a translator. It translated the general hope of lift into the specific behavior of the Wrights' own designs. It translated disappointment into diagnosis. It translated the old tables into a more limited truth, valid here, uncertain there, misleading if stretched too far. This was part of the technical rivalry at the heart of the story. The Wrights were not competing only with other inventors. They were competing with inherited assumptions. They were competing with the temptation to believe that an authoritative table could substitute for an experiment shaped around their own machine. The tunnel gave them a way to stop guessing at that boundary. In Dayton, the idea of a wing became more disciplined. It was not simply a curved plane. It was a curved plane of a certain camber with a certain span, a certain chord, and a certain relationship between the two. It had to lift, but it also had to move forward without too much penalty. It had to be large enough to carry a pilot, but efficient enough to be manageable. It had to belong not to aviation in the abstract, but to the particular flying machine the Wrights were trying to create. Aspect ratio also connected the wind tunnel work to the larger problem the brothers had never abandoned: control. A better wing was not enough if the pilot could not command the aircraft. But a better wing could make command more meaningful. If the glider produced lift more efficiently, if its surfaces behaved closer to expectation, then the pilot's actions could be tested against a machine that was no longer fighting bad assumptions at every moment. The 1902 glider would carry these lessons out of the shop and back to the wind. It would not be just another enlargement of earlier hopes. It would be a machine shaped by measured evidence, low camber curved surfaces, improved proportions, and a new understanding of why old data had failed when applied too broadly. The long wings were not an aesthetic choice. They were the result of a contest between inherited tables and the Wrights' own balances. And in that contest, the balances had won. By the time the brothers moved from the wind tunnel toward the next glider, they had done more than correct a calculation. They had changed the relationship between design and proof. A wing was no longer accepted because a respected source implied it should work. It had to earn its place in the machine. It had to answer in the tunnel before it answered over the sand. The old tables had brought the Wrights into flight research, but the long wings showed how far beyond those tables they now had to go. The next machine would carry that evidence into the air. And there, at the Kill Devil Hills, the question would widen again. The wing had to lift. The proportions had to work. But the pilot still had to command the whole craft, and the glider would have to prove that measured lift and active control could finally belong to the same machine. The next machine would carry the tunnel's evidence back to the sand. That was the quiet importance of the 1902 glider. It was not simply another step in a sequence of kites, gliders, and experiments. It was the first large Wright machine built after the brothers had forced their doubts through a controlled measuring instrument. The wind tunnel in Dayton had not given them flight by itself. It had given them choices. It had helped them decide what kind of wing curvature was worth using, what proportions were more promising, and why older aerodynamic tables could mislead when applied to a different wing shape. Now those choices had to leave the bicycle shop. At Kitty Hawk and the Kill Devil Hills, the air would not be as orderly as the air inside the wooden tunnel. It would shift, gust, and roll over the dunes. Sand would move underfoot. The pilot would lie in the machine and feel the glider respond, not as a model on a balance, but as a full craft in a living wind. If the tunnel numbers were useful, they had to become something more than readings. They had to become behavior. The 1902 glider incorporated the results of that tunnel campaign. NASA states that it had roughly the same wing area as the 1901 glider, but about twice the aspect ratio. That detail is easy to pass over, but it marked a major change in judgment. The Wrights were no longer simply increasing size in the hope that more surface would solve the problem. They were changing the shape of the lifting system. The long, thin wing had won its argument in the tunnel, and now it appeared in the machine they took back to North Carolina. The glider also carried the lesson of camber. The brothers had learned that curved surfaces could produce more lift than flat ones, but that more curvature could also bring more drag. The useful answer was not an exaggerated curve. It was a measured one. NASA states that the Wrights settled on a 1/20th camber for their designs. In the 1902 glider, that was not an abstract preference. It was part of an aircraft built around a new relationship between theory and proof. Shape had been tested. Numbers had been compared. Old assumptions had been narrowed and corrected. But the chapter of the glider that mattered most was not written only in lift.
From the beginning, Wilbur and Orville Wright had treated flight as a problem of control, as much as a problem of support. They did not believe the answer was simply to build a surface large enough to rise, attach an engine, and hope stability would take care of the rest. Their glider work had taught them that a pilot would have to command the machine. Flight would not be a passive condition. It would be an active act. This was where the 1902 glider became decisive. The Wrights already had wing warping, their method of twisting the wings to change lift from one side to the other. In principle, this allowed the pilot to roll the craft, lowering one wing and raising the other. But control in the air was not a collection of separate tricks. One movement could create another problem. Changing the lift on the wings could also affect the way the machine turned or yawed. A glider that could be rolled but not coordinated could still fight its pilot. The 1902 machine helped the brothers solve this control problem with a movable rear rudder connected to the wing warping system. This connection mattered. The rudder was not merely a fixed fin placed behind the glider. It was movable, and it worked with the wing warping rather than apart from it. The machine was becoming an integrated control system. Roll and yaw were no longer treated as unrelated effects. They were linked in the hands and body of the pilot, or more precisely, in the pilot's hips. The Wrights operated the control system through a hip cradle. The pilot lay prone on the lower wing, reducing frontal resistance and placing his body within the structure of the machine. By shifting his hips in the cradle, he could operate the wing warping and the connected rear rudder. The arrangement was practical, compact, and deeply revealing. It showed how the brothers thought about flight. They did not imagine the aircraft as a stable platform that merely carried a person. They imagined pilot and machine as one working system. That was the fusion. Measured lift from the wind tunnel, better wing geometry from the aspect ratio studies, active control through wing warping, the movable rear rudder, and the hip cradle. Each idea had importance on its own, but the 1902 glider brought them together in the air. The machine was not only designed to rise, it was designed to be flown. The distinction is essential. Many experimenters had pursued lift. Some had built models that flew. Some had built machines that seemed promising in drawings, demonstrations, or partial tests. The Wrights were after something more demanding. They needed a full-scale craft that could carry a pilot and answer commands. In that sense, the breakthrough of the 1902 glider was not simply that it could glide farther or behave better than the machines before it. The breakthrough was that the pilot could begin to command the whole craft in a coordinated way. This was the war before the first flight, reaching one of its turning points. The Wrights had fought against the uncertainty of published data. They had fought against the mismatch between prediction and performance. They had fought against the temptation to treat failure as proof that flight itself was out of reach. By the time the 1902 glider flew at the Kill Devil Hills, the conflict had changed. They were no longer asking whether the old numbers were trustworthy. They were testing the machine built from their own numbers. And the result gave them something more powerful than confidence. It gave them a method. If the glider did not behave as expected, they could adjust and test. If the control response exposed a new problem, they could modify the mechanism. Their approach was not a single leap from ignorance to success. It was a disciplined chain. Observe, measure, build, fly, correct. The wind tunnel had made that chain stronger because it gave the brothers a way to separate guesswork from evidence before committing to a full-size design. The 1902 glider also clarified why propulsion had waited. To an outside observer, the absence of an engine might seem like incompleteness. But for the Wrights, the glider was the necessary proof that an engine would not be wasted. Power could make a bad aircraft more dangerous. It could drive an uncontrollable machine faster into failure. Before the brothers added a motor, they needed to know that the wings could lift efficiently and that the pilot could govern the craft. The 1902 glider moved them toward that answer. This is why the machine belongs at the center of the story, even though it was not the famous flyer of 1903. It was the bridge between aerodynamic correction and powered flight. The wind tunnel had changed the wing. The glider proved that the changed wing could work in a real wind. The control system then showed that the machine could become responsive, not merely airborne. At the Kill Devil Hills, the Wrights were still working without the kind of institutional weight that surrounded other aviation efforts. Their laboratory was divided between a Dayton bicycle shop and the exposed dunes of North Carolina. Their instruments had been shop-built,
Their model wings had been cut, hammered, filed, and soldered from materials close at hand. Yet the 1902 glider showed that careful measurement could compete with reputation, and that a small workshop could produce knowledge strong enough to reshape a full-size aircraft. The pilot's command was the crucial point. A glider that lifted but wandered beyond control was not the answer. A machine that depended on luck, or on perfect wind, or on passive balance alone could not become practical flight. The right solution made the pilot part of the machine's intelligence. The hip cradle translated bodily movement into aerodynamic correction. Wing warping altered the lift across the wings. The movable rear rudder helped coordinate the response. The machine did not simply endure the air. It negotiated with it. By the end of the 1902 season, the brothers had done more than improve a glider. They had brought together the central ideas that had been forming since Wilbur first entered the aeronautical conversation through the Smithsonian's recommended reading. They had taken the inherited problem of lift and tested it. They had taken the old dream of stability and recast it as active control. They had taken the shape of the wing out of the authority of tables and placed it inside a cycle of measurement and trial. The first powered flight was still ahead. The propellers, the engine, and the final machine would introduce new problems. But the foundation had shifted. The brothers now had a controllable aircraft form, and that changed the meaning of everything that followed. Power would not be added to a mystery. It would be added to a machine whose lifting surfaces, proportions, and control system had already been disciplined by experiment. Far from Dayton in the Outer Banks, another path to flight was moving under a very different kind of roof. Samuel P. Langley, Secretary of the Smithsonian, had already achieved successful powered model aerodrome flights in 1896. His work carried institutional prestige, scientific authority, and national attention. Soon, his full-scale human-carrying great aerodrome would be brought to the Potomac River for its own trial. The Wrights had a glider a pilot could command. Langley had a rival machine with the weight of the Smithsonian behind it. And the question of who truly understood flight was about to move from workshops and dunes into public view. The Wrights had come to power by a narrow and disciplined road. They had not begun with an engine and then asked the air to make room for it. They had begun with lift that failed, tables that disappointed them, a coefficient that had to be questioned, and a glider that gradually became obedient under a pilot's body. By the time their work pointed toward a powered machine, the essential shape of their method was already clear. Langley's road looked different from the beginning. Samuel P. Langley was not an obscure experimenter working behind a bicycle shop counter in Dayton. He was Secretary of the Smithsonian Institution, a position that placed him near the center of American scientific authority. His aeronautical work had the weight of an institution behind it, and, for good reason, it attracted attention. In 1896, Langley had achieved successful powered flights with model aerodromes. These were not human-carrying airplanes, but they were important. They showed that a powered model could leave its launching apparatus and sustain itself in the air. For anyone watching the race toward flight, that mattered. Langley had demonstrated something visible, mechanical, and persuasive. A powered flying model had worked. The path from that achievement to a full-scale machine may have seemed from a distance like an enlargement problem. Build a larger aerodrome. Give it an engine. Place a person aboard. Launch it into the air. But the history of flight was becoming a history of scale, and scale was unforgiving. The Wright brothers had learned this lesson from another direction. Published aerodynamic data had not simply enlarged into their machines. Lift predictions that looked convincing on paper had not matched their gliders at Kitty Hawk. Otto Lilienthal's data, they eventually came to understand, was largely valid for the wing geometry from which it had been derived, but not directly transferable to their own long, thin, rectangular planforms. A wing could not be understood only as an abstract area. Its camber mattered. Its aspect ratio mattered. Its drag mattered. Its control system mattered. The pilot's ability to command the machine mattered. Langley's successful models had proved that model flight was possible. They did not prove that a full-scale human-carrying aircraft would fly. That distinction became painfully public in 1903. Langley's full-scale human-carrying aircraft was called the Great Aerodrome. Its trials did not take place on the open sand of the Outer Banks, where wind, distance, and repeated gliding practice had shaped the Wrights' work. They took place on the Potomac River from a houseboat. This alone gives the scene a different character. The Wrights had walked their machines over dunes and launched them into coastal winds. Langley's great aerodrome was to be sent outward from a floating platform near the nation's capital, in view of a different kind of audience and under the shadow of a great public institution. The first of Langley's 1903 full-scale launch attempts came on October 7th. The machine was launched from the houseboat on the Potomac River. It did not fly. The great aerodrome failed in the attempt. This was not yet the end. Experimental failure, by itself, did not separate Langley from the Wrights. The Wright brothers had failed repeatedly. Their 1900 and 1901 gliders had not performed as predicted. The bicycle wheel test in Dayton had produced results difficult to control. Their path had included confusion, frustration, and reconsideration. Failure was not the difference. The difference was what kind of failure a machine exposed. For the Wrights, failure had forced measurement. It had driven them into the wind tunnel, into balances, into comparisons among small wing shapes, into revised aerodynamic values, and into a glider that gave the pilot a more complete system of command. Their failures had been turned inward, into a process that made the next machine more intelligible. Langley's great aerodrome was testing something far more complete and far less forgiving. It was not only asking whether a powered structure could produce enough lift. It was asking whether the full-size arrangement could survive launch, enter the air properly, and sustain human-carrying flight. The National Air and Space Museum states that Langley's great aerodrome proved incapable of flight in its 1903 attempts. That judgment is important because it keeps the issue fixed on the actual trials, not on promise, reputation, or later speculation. In the attempts that mattered, the full-scale machine did not fly. A second attempt came on December 8, 1903. By then, the year was nearly over, and the Wright brothers were close to their own powered tests at Kitty Hawk. 9 days separated Langley's second failure from the first successful Wright flight. The proximity can make history feel like a contest decided by a narrow margin, as if one machine simply arrived a little earlier than the other. But that is not the deeper lesson. The two programs had not merely been racing along the same track. They had been shaped by different understandings of what the problem of flight required. Langley's advantage was real. He had standing, funding, institutional credibility, and the earlier success of his powered models. In an age when aviation remained uncertain, those things were not trivial. The Smithsonian name carried authority. A model aerodrome that had flown in 1896 gave observers a reason to believe the larger machine might succeed. Langley's work belonged to the visible world of scientific ambition, public recognition, and national expectation. The Wrights' advantage was quieter. It lay in the harsh discipline of mismatch. Their early gliders had refused to obey the numbers they had borrowed. Instead of treating that refusal as a minor defect, they followed it to its source. They questioned the Smeaton coefficient. They tested airfoils in a controlled stream of air. They learned that curved surfaces gave more lift than flat ones, but also more drag. They selected low camber. They learned that long, thin wings with high aspect ratio could perform better than short, wide wings. They built the 1902 glider around those findings, and then joined wing warping to a movable rear rudder through a pilot-operated control system. By the time power entered their design, it entered a machine already educated by experiment. This is why Langley's great aerodrome belongs in the story before Kitty Hawk. It is not merely a rival machine standing off to the side. It clarifies what the Wrights had actually achieved before their engine-driven flyer left the rail. The Wrights were not only trying to add horsepower to wings. They were trying to create an airplane in which lift, drag, propulsion, structure, and control could work together under a pilot aboard. Langley's earlier powered models had shown that mechanical flight was not fantasy. But the great aerodrome's failures showed that a successful model did not automatically become a successful airplane. The passage to full scale was not a simple multiplication. Weight changed. Structural demands changed. Launch conditions mattered. The pilot transformed the problem. A human-carrying aircraft had to be more than a promising arrangement of surfaces and power. It had to leave the ground, remain intact, sustain itself, and be controllable. On the Potomac, in October and December of 1903, institutional force met that reality.
The machine had a distinguished sponsor. It had a lineage of model success. It had public importance. But in its full-scale trials, it did not become an airplane. At Kitty Hawk, the Wrights were preparing a different test. Their machine would not be backed by the same public institution. It would not emerge from the Smithsonian's official authority. It would come from Dayton workshop practice, Outer Banks gliding, wind tunnel data, and a control system refined through bodily experience in the air. The contrast is not between science and tinkering. That would be too simple, and it would misunderstand both sides. Langley was a serious scientific figure, and the Wrights were serious researchers. The contrast is between two forms of evidence. One had the prestige of an institution and the memory of successful powered models. The other had a chain of hard-won, full-size lessons leading toward a machine a pilot could actually command. As December 17th approached, this quiet difference was about to become visible. The question was no longer whether flight could be imagined, modeled, or promised. It was whether a powered airplane, with a person aboard, could lift from the earth and fly under control. By the morning of December 17th, the question had narrowed to a strip of sand, a wooden rail, a headwind, and a machine that carried years of argument inside its frame. The Wrights had already learned that flight would not yield to confidence alone. It had resisted published tables, exposed errors in expectation, and forced them back into their Dayton shop to measure what the air was actually doing. Now the answer would no longer be read from a balance inside a box of moving air. It would have to appear in the open at Kitty Hawk, North Carolina, with a pilot aboard. The machine waiting on the sand was the 1903 Wright Flyer. The National Air and Space Museum identifies it as the first successful powered airplane with a pilot aboard. That description matters because it contains several conditions at once. It was not only a glider. It was not only a powered model. It was not only a machine launched without a person responsible for controlling it. It was an airplane, powered, carrying a pilot, and capable of leaving the ground in sustained, controlled flight. Its form still carried the logic of the brothers' earlier experiments. The Flyer was a canard biplane with the horizontal control surface forward, the wings arranged one above the other, and the pilot lying on the lower wing. Its structure was made from a wood airframe covered with muslin fabric, with an aluminum engine crankcase as part of the power plant. The National Air and Space Museum gives its wingspan as 40 feet 4 inches, its length as 21 feet 1 inch, and its empty weight as 605 pounds. These measurements can sound like museum labels, but in the story of the Wrights, they are also a record of compromise. Every foot of wing, every pound of structure, every surface exposed to the wind had to answer to the hard lessons of lift, drag, weight, and control. The engine was modest by later standards, but decisive in this moment. The Flyer used a 12-horsepower Wright horizontal 4-cylinder engine. That engine drove 2 pusher propellers through a sprocket and chain transmission system. One chain was crossed so that the 2 propellers rotated in opposite directions. Here again, the machine was not a single invention, but a gathering of connected solutions. The brothers had needed enough power, but not power in isolation. They needed propellers shaped with aerodynamic understanding. They needed a transmission that could deliver motion to both propellers. They needed the airplane to remain controllable once it began moving through the air under its own force. A 60-foot starting track was laid south to north into the north wind. The wind that had brought the Wrights to the Outer Banks now became part of the final apparatus. Kitty Hawk and the Kill Devil Hills area had been chosen because Dayton did not offer the steady conditions the brothers needed. For years, the coastal air had served as an outdoor laboratory. It had revealed disappointment, then allowed practice, then accepted the 1902 glider as a machine that could finally be commanded. On this December morning, that same environment would test whether the powered Flyer could join lift, propulsion, and control in one act. At about 10:35 in the morning, according to the National Park Service, Orville Wright made the first successful takeoff. Wilbur ran near the right wingtip as the machine moved along the track. John T. Daniels of the Kill Devil Hills Life-Saving Station stood with the camera, prepared in advance, and took the famous photograph as the Flyer rose. The image has become so familiar that it can seem almost inevitable. But the photograph captured something deeply uncertain, a fragile machine just above the sand, a man lying prone at the controls, and another man watching from the ground
as years of private calculation became public fact. The first flight covered about 120 feet in 12 seconds in strong winds.
The distance was short. The time was brief. Yet the meaning was not small.
In those 12 seconds, the flyer did what Langley's full-scale great aerodrome had not done in its 1903 trials on the Potomac River. It carried a human being into the air, under power and control. It turned the Wrights' chain of evidence into an event that could not be reduced to theory, promise, or institutional prestige. That first flight was not the end of aviation's problems.
It did not make flying simple.
It did not erase the dangers of early aircraft or settle every technical dispute.
But it crossed a boundary. The Wrights had shown
That a powered airplane could be built from measured aerodynamic data, practical mechanisms, and an active system of control. Their victory had been prepared before the engine ever pulled the machine forward. It had been prepared in the decision to distrust results that did not match reality, in the wind tunnel balances, in the testing of small wing shapes, in the revised understanding of lift and drag, and in the discipline of learning how a pilot's body could command a machine in unstable air. This is why the Kitty Hawk flight belongs to the wind tunnel story, not as a separate miracle, but as its consequence. The brothers had not simply added an engine to a dream. They had earned their way to the engine through measurement. They had learned that the air did not reward reputation. It rewarded accurate surfaces, useful proportions, enough thrust and control that worked when the machine was no longer safely on the ground. Yet even after December 17th, the question of credit did not rest quietly. The rivalry with Langley and the Smithsonian did not end cleanly with the flyer's success. In later years, a controversy developed around the Smithsonian's display of Langley's aerodrome. Smithsonian officials displayed the aerodrome with wording that implied Langley had built a machine capable of flight before the Wrights. To Orville Wright, this was not a harmless ambiguity. It touched the central claim of the entire struggle. If Langley's machine were presented as already capable of flight, then the distinction between powered model success, failed full-scale trials, and the Wrights' controlled human flight would be blurred. The point was not that Langley had done nothing important. He had achieved successful powered model aerodrome flights in 1896, and his work was part of the serious aeronautical effort that preceded the airplane. But the National Air and Space Museum states that Langley's full-scale human-carrying great aerodrome proved incapable of flight in its 1903 attempts. That distinction was the heart of the matter. A model that flew, a full-size machine that failed, and a piloted airplane that succeeded were not the same historical fact. Orville's response was severe and symbolic. He sent the 1903 flyer to the Science Museum in London. The airplane that had first flown at Kitty Hawk left the United States because its surviving maker believed the Smithsonian had not honestly renounced a competing claim. Only after the Smithsonian renounced the implication that Langley had built a machine capable of flight before the Wrights could the flyer's place in the American national story be repaired. This afterlife of the claim reminds us that invention is not only the moment when a machine works, it is also the struggle over what counts as proof. The Wright brothers had fought that struggle first against numbers that would not fit, then against the uncertainty of wind and sand, then against a better-funded rival machine, and finally against the language used to describe the past. Their achievement depended on careful experiment, but its memory depended on careful wording. At Kitty Hawk, the first flight lasted only 12 seconds. But those seconds carried the weight of years, the letter to the Smithsonian, the borrowed books, the gliders that disappointed them, the coefficient they revised, the wind tunnel they built, the small wings they tested, the control system they trusted, and the powered machine that finally rose. The war before the first flight was not loud. It was measured in lift, drag, camber, aspect ratio, chains, propellers, and the judgment to let evidence overrule authority. And in the end, the air answered in the plainest way it could. The flyer moved forward, lifted from the rail, crossed a short distance above the sand, and proved that the problem had been solved well enough for a human being to fly.